Okay, we have success. But before I jump ahead, I want to walk you through quickly how I got here. Now, I'm not going to describe everything because it could take hours, and there are some really good YouTube videos that describe all the capabilities of what I'm going to talk about here. But the key thing to Atmel Studio, and this thing understands something like over 650 different chips and boards that they make, full board solutions, is this feature here, Atmel Start. You do not want to hand twiddle every bit on a serial port chip to make it work. You want to use this tool to add the functionality that you want so you can focus on what your code needs to do. Now, I'm kind of torn because I'm not a big fan of tools generating your code for you, because if there's a bug in the tool, you're screwed. And sometimes the tool keeps you too far away from the thing you're trying to do, and it doesn't give you enough control. But in this case, we really almost have no choice. You could try and write this stuff by hand, but it's just not worth it. Now, the key thing is, so here's my project, DC current sensor with CANBus output. I have added an analog to digital controller, and it has named it ADC0. Fine. But I'm going to show you some of the other things that you can add to your project based on what you've got installed in your hardware. First thing I'm going to do is walk you through the drivers. Now, these are basically chip level functionality of things that you can turn on and turn off inside the MCU on your board that you bought from Atmel. So analog comparators, that means you've got two different signals coming in on two different pins, and it will compare those two values. Or an analog to digital converter, and that's what I did. That's one signal coming in on one wire, convert it to an analog, from an analog signal to a number, then I can work with that number. A 12-bit ADC will give you a value of 0 to 4096, because 2 to the 12th is 4096. The CANBus feature I will be implementing later, and that turns on the CANBus feature of the chip and allows you to construct and send and receive messages on the CANBus. It's got things like calendar handling, digital to analog converter, so that's the other way. I've got a number 637. I want to turn that into an analog signal. It's got delays, it has events, handle external interrupts, read and write from flash memory, frequency counter. I2C is a serial bus that's used for chip-to-chip communications. Touch controllers, PWM, pulse width modulation, that you can say send out a square wave but give it a 10% duty cycle, and you can play with the duty cycle to generate what you want. SPI is another chip-to-chip interface. Temperature sensors, timers. The USART is the, or UART as it is also known, is basically an external serial port, and that's what I'll use to connect up my USB chip. The other thing that Atmel Start can do is provide higher level functionality above the chip level and give you access to software for these kinds of things. So here's a data protocol, real-time clocks and calendars, cryptography. They have chip support for encrypting and decrypting your data as it comes in and out of the chip, which is amazing. It's very, very secure. It has graphics drivers for different kinds of displays that you can connect to the system. It has what are called HMI, human-machine interfaces. So this is things like a thumb control like you would have on a video game console, touch pads. It will encode and decode JPEG graphic images for you. Different kinds of interfaces. Here's the CANBus interface, RS-232 serial port interface. It can control relays for you. It can control motors, motor drivers. It can control fans. It has network protocols, including a full TCP/IP stack, so you could connect your device to the internet, and this would handle everything for you for internet protocols. And it also has an entire real-time operating system called FreeRTOS. A real-time operating system is kind of like Windows or Mac OS, but the real-time part of it means it will respond within microseconds to an external interrupt. Or if you have a timer that's set to go off every 100 milliseconds, it will fire every 100 milliseconds, and it guarantees that. You will never have any timing-related issues, which something like Windows and Mac and Linux cannot provide for you. It has sensor input, it has USB devices. You can talk with a USB device like a camera or a hard disk, and it provides really great high-level functionality for you simply by clicking and adding it to your project. But the thing that I need to read my signal from the current sensor is an analog to digital converter. Now I've added one to my project, but let's take a look at how I've configured it. So we click on the little gear and we scroll down. And here are the factors that I can select as part of how I want that analog to digital converter set up. Now, there's a few different ways you can make this work, and it all comes down to how do you want to read the data. I want to read it asynchronously, which means I want to make a request that says, please read some data, and then at some point later, the system comes back and says, here's your data. Now what that does is it allows my code to continue running and doing other things while the chip is reading my current sensor signal for me, as opposed to sync, which is synchronous, which the code that I'm running would halt waiting for that response to come back. So we definitely want async. Now, here's the section where it maps the function to the pin on your chip. I have wired to pin 3 of my chip, which maps to PA0, which is the analog input channel 0. So just by checking this box, I have mapped an abstract function inside the chip to a specific pin number, and that's key. That's what I didn't want to have to do by hand. Now, here's more things we can do. I have a choice of how fine a resolution I want to be reading my samples with. 12 bits is the native capability of the chip, so that's what we're going for. We can dumb it down to 8 or 10, and we can extrapolate it to 16, but we're just going to stick with 12. Now this is key. This says when you're reading, how do you want it to compare? If 4096 is my maximum reading, we have to have a value that defines what 4096 is so I can compare it. And what I've done is I've said compare it to, on the circuit board, I've also hooked up 5 volts to the VDD analog pin. So basically, every sample I'm taking, I'm comparing its maximum value to 5 volts. And that's exactly what we want. We don't need to worry about the clock. And again, we select our positive input selection is that pin, the AIN0, and the negative value is going to be ground. So basically, I'm asking it to sample my voltage and convert it to a number from 4096 and 0. 0 is ground, 4096 is 5 volts. I simply set all this and click Generate Project. And it produces all of these files over here for me. The only code I've written is in this file main.c, and I'll walk you through that now. Okay, we've got the board hooked up for the first time. We've got it connected to the 12 volt DC power supply. We're making 12 volts. We've got the board plugged into the Atmel ICE over the 10-pin SWD bus.
which I was clever enough to put in because my USB don't work. The Atmel ICE is plugged in to the USB of the laptop, and I'm running Atmel Studio version 7. So let me pop over and do the screen recorder and we'll see what happens.
We can also see up here that I'm currently working with an ATSAMC21E18A. It knows everything about this chip, and it knows how to talk to it, and it actually points me to the documentation for the chip and the supported tools that go along with it. And right now I'm using this Atmel ICE device. And you can see we've currently got the Atmel ICE is plugged in, and I think that's the serial number of the board, and I'm talking to it over the SWD bus, and everything's good. Now if we go up here, this is the device programming section. I've got Atmel ICE talking to my C21E18A, and I'm going to say apply. Okay, so we're now hopefully talking to the board. I'm going to read the voltage, 5 volts on the board, which is lovely, and we're going to read the device signature. So that's good. We didn't get any errors, and we get a device signature of hex 0x1101030A, which is the device signature of that chip. So we know that the chip matches what the Atmel ICE is expecting. We're looking at all this device information. Okay, so it's telling me that's my device, and we're on revision D of the actual silicon of that chip, or perhaps the, I don't even know what to call it, the micro firmware that's burned into the silicon. It tells me this is my Cortex CPU. I've got 264K of flash. I've got 32K of RAM. Here's my voltage levels. Here is my, you can actually take a snapshot of the memory and read it into your PC and examine it that way, or write a block out to your device, which is nice for, say you're making 1,000 of these things. It's a good way to load the firmware into each board. Then the system has this thing called fuses, which you can set or clear that perform certain functions for you. I don't think I need to get into that. And then there's also a security bit. If I click set, my firmware is locked into the board and it can never be read externally, and that's to reduce the chance of someone reverse engineering your software. Okay, we're in Atmel Studio and we're about to run this piece of code. It's very simple. All it does basically is initialize all the Atmel stuff. They provided that for me. And then in this while loop, all I do is increment this count variable by 1. It's going to go 1, 2, 3, 4, 5, 6, 7. And then when it hits 100, it's going to say loop increment by 1 and reset the count by 0. This is meaningless code, but I want to show you the demonstration of how you can actually debug your hardware using the setup that I've got. Now, one thing I found initially was it wouldn't stop at a breakpoint on this line, but when I went into the configuration under the compiler optimization, it was set to optimize to level 1, but when I turn optimization off, now I can breakpoint on this line. So if I click here, it's going to stop the code running in hardware on that chip when it wants to add 1 to the variable called count. So let's go ahead and run it. I'm going to click on the Start Debugging icon. Down here in the compile code, it's going to load it through the chip, and then it's going to begin execution. And here we are. We are now stopped at the breakpoint for this line right here. And you can see down here, we've got our 2 variables, which are shown down here. They both start off with a value of 0. If I click on the step over icon or hit F10, we have now added 1 to the value of count. So that's great. We're actually running code in the chip, and this is just 10 minutes ago, I got this to work for the first time. So not only is my board wired up right, manufactured correctly, I've got the Atmel ICE talking to the board through the USB and being driven by Atmel Studio. So everything is coming together. The fact that I can add 1 to this variable is meaningless, but it tells me my entire development setup is working properly, and now I can do real things. So I can just go up 2, 3, 4, 5, great. But what about if I want to test out what happens when I hit my if count equals 100 section? I can actually down here change the value of my variable. It's now 99. And I'm going to come around and we're going to increment and we're going to come around. The value is now 100 and we are sitting inside this loop right now. This is the first time we've come into this loop. We're going to add 1 to the variable loop, which just happened right there. We're going to reset count to 0 right there. And we're going to come back around and add 1 to count, which just happened. So everything is good. Now all I have to do is start reading current values and sending CANBus messages. Okay, here's all the code I've written is in main.c, and I'll walk you through that now. Now I like to comment the crap out of things so I can remember what I did later, but also if anyone else is using this code later, they can understand what's going on. So basically what I did is I put a giant comment in here about all the things I selected in the Atmel start for my analog to digital interface. That way, someone can find my main code and recreate all of this generated code simply by selecting the same thing I did up here, purely for reference of how the tool was set up, because if you don't have the original tool definition, you're kind of screwed. So let's jump down to the main loop inside the code. So the first thing we do is we call Atmel start init. This is provided by the tooling, and it initializes all of the hardware based on the things that I have selected in Atmel start. One line of code, the entire chip is configured exactly the way I want it. So that's great. Now, specifically, I want to initialize my current sensor input channel. So I wrote a little routine for that, and we'll jump back up here and look at that. It is right here. This is actually provided as sample code over here in one of these files. You just copy it and paste it into your program. And you can change the names around and play around with the variables. But basically, what this is going to do is register. Okay, we'll skip that for a minute. We're going to enable the channel for analog to digital sampling. And we're going to say start conversion. So basically, give me my first sample, or start reading and then let me know when my sample is ready. And it lets me know my sample is ready through this callback function, which I've called current sensor callback, and I register that function with this method. So when the conversion is complete, the code will call this method and then I do my thing. Now, this is the callback method right here. When it comes in here, all I do is set this global variable conversion complete is true. That signals my main that a value has been read all the way through the hardware and it's ready for you. So we'll come back down here. After I do my initialization, I delay for half a second and then I call start conversion. That's kind of redundant to what I did above, but every time I go through the loop, I have to ask for please give me another analog to digital value. Now, this loop here says while the conversion is not complete, you'll notice the exclamation point means not. This box means do nothing. So it just sits here and spins while we're waiting for the conversion to complete. When my callback function sets that true, we immediately drop down a little bit in the code. I set the flag false in preparation for the next loop, and then I say read channel from ADC0 into this variable, ADC result, and that's 2 bytes. Now I've asked for 12 bits of resolution, so I need at least 2 bytes to store it. 2 bytes is 16 bits, so 12 bits will happily fit in there. Now, because of the way the values come back in those 2 bytes, if I want to make a single recognizable number from it, I have to take the second byte, shift it over by 8 bits, and then slot in the first byte. And this is pretty common when you're dealing with raw memory access. So now I have my current sensor raw input value. This is my number from 0 to 4096. I then call a method with that number to convert my raw sensor value into my real current value. And I get that number back here. And then I call a CANBus method that I wrote that will put this value on the CANBus. So let's take a look at my conversion function. Okay, here's my conversion function. Basically, the purpose of this is to convert from 0 to 4096 to negative 50 amps to 0 to positive 50 amps. So since we have a 12-bit input, each full amp, because it's a 100 amp span, is equal to 40.96 input points, or we might round up to 41. Therefore, 1 point of incoming resolution from 0 to 4096 is about a 40th of an amp, or 25 milliamps, which should be sufficient for our purposes of riding an electric motorbike. Now, what I'm going to do later is have a calibration function which will allow me to set the correct 0 value and the correct 50 amp value, which will make this calculation much more accurate based on the characteristics of the current sensor chip and the wiring and everything else. But basically what we're doing is we've got this number which is halfway between 0 and 4096. This is our calibration offset. This is our 0 amps value, from negative 50 amps to 0 to positive 50 amps. And then the full scale value of 50 amps, either negative or positive, is also 2048. And the full amperage is represented by 50 amps. Now, what we first want to do is figure out how far away from 0 we are. Either positive or negative is irrelevant. So we take our raw input and we subtract the offset from it. Then we take the difference from 0, we divide it by the full scale of the calibration, which is 2048. Then we multiply it by our 50 amps maximum value. There we end up with our calculated amps, from negative 50 to 0 to positive 50. And then that's what gets sent back to main.c, and that's what gets sent to the CANBus function. Now, at this point, the CANBus function is not implemented.
Okay, let me walk you through the physical hardware setup. My 60-volt power supply is going to be driving the current under test into the board. But in order to put some load on it, I've pulled over my JevQ test bench here, but I'm only using these light bulbs. That's the only thing in the circuit. I come out of the 60-volt supply, through the lights, come up here, through the board, through this meter, which will be measuring amps, and we can compare that against what I'm getting in my code. And this meter is measuring the analog output of the current sensor chip. So that should be 2.5 volts should be 0 amps, 5 volts would be 50 amps. But because of the way I've got these light bulbs working, we're only going to get 1.7 amps out of this. So this should say something a little bit over 2.5 volts. This should be around 1.7 amps, and we should be reading about 1.7 amps in the code. So let's give it a try. And contact. Okay, we've got a lot of light and a lot of heat. We've got 1.7-ish amps flowing through and 2.57 volts on the output of the chip. So that's 7/100ths of a volt above zero. So let's take a look and see what we're getting in the code.
Okay, we're in the code. I've set a breakpoint right after the sensor value conversion function. So every time we hit here, we should see our current sensor calculated amps will be displayed down here. So let's run the debugger. It's building the code, it's executing it, and okay, our first values just come in, 1.269 amps. Let's go again, and again, 1.07, so we're getting some bouncing around a little bit, 1.12, same, 1.123, same, 1.22, oh, 0.87, 1.5. So you can see that we're going to need a smoothing function here because things are bouncing around quite a bit, and we're not really very close to our 1.7 amps that is really flowing through there. So you can see where the need for the calibration offset and scale factors are going to come into play. But the good thing is we're getting readings from the hardware, and it's telling me I've got a little over an amp flowing through. Now let me hit and turn off the 60 volt power supply. That's going to take us down to 0 amps. You can hear the power supply fan just went off. And my next sample, dropping down, yep, it thinks we're now negative a half an amp. Negative half an amp. Negative a little bit under the 0 point. So that's where the scaling and calibration comes in. Now if you think about it, if we take 0.46 and we add it to the 1.2-ish numbers we saw coming through, that's pretty darn close to 1.6, 1.7 amps. So if we can get our 0 offset here through calibration, I think this is going to work out. So that wraps it up for this edition. I'm going to go redo the circuit board. I've got a few things to fix. The package company, ATSAMC, that makes the component packages with the schematic symbol and the PC board layout, they came back with literally within hours, right after they woke up in England, saw my report, fixed them, and sent me an update. So I give them huge props for being so responsive.
Another thing to consider, as I was waiting for the boards to come back from China, I had a thought. Why don't I add voltage measuring functionality to the board too, so it measures both voltage and current of the same circuit. That way you can calculate power, and that makes a good independent device that you can stick in nearly any project, and you get the two most important factors for the wire that you're interested in. So I have to look at the way I would need to read voltage into the microcontroller, and if I have to do a voltage division kind of a thing, because it can only read up to 3.3 volts or 5 volts, so I would have to scale it down. I'd have to condition it to make sure it didn't destroy the microcontroller, and there's some other factors that come into play. I think that's a good thing to add to version 2 because it makes it more of a complete independent device that provides so much more functionality.
As you stare out on my beach, I would ask you to subscribe to my channel and click like on this video so YouTube thinks I'm worthy again, and I have so many people on my channel that they'll give me 10 cents a day in ad revenue. So I thank you for that.